Okay, we have covered the first part of principal component analysis of the first 44 slide that shows how to find the principal axis and the scores by using the iterative method and QR factorization and singular value decompositions. Okay, today, we continue the second part of PCA. And these are the materials that I have used, and this is the material that I made for you to practice what we have done. First, review. PCA provides a mechanism to recognize data's geometric similarity through algebraic means. Here, the matrix S is symmetric, so it can be orthogonally diagonalized. This connection between statistics and linear algebra is the beginning of principal component analysis. Okay. Here we started with the covariance matrix, which is symmetric, and we used the eigenvalues and eigenvectors to find the principal axis, and this connection is the key idea of principal component analysis. Okay, as we recall, then. By applying the theories, then the eigenvalues of the matrix in the decreasing orders, and this corresponding also normal eigenvectors UIs. And these eigenvectors are called the principal component of the data set. And total variance T. Here, the trace of the matrix S is in sum of the diagonal entries of S, which is the sum of the variances of all m variables. We call this total variance, which is the sum of the eigenvalues, which is same as the trace of the matrix S. Okay. The direction in Rn given by the vector U1, that's the first principal direction, explains an amount lambda1 of the total variance. What fraction of the total variance? It is lambda1 of the sum of all eigenvalues, the trace of A. And this fraction, this ratio, this is the key that we're going to use. Similarly, the second principal direction accounts for the fraction lambda2 of T, total variance, which is the sum of the eigenvalues of S, and so on. So we can find that we can use those. The vectors U1 point in the most significant direction of the data set. Okay, and among directions that are orthogonal to U1, U2 point in the most significant directions of the data set. Among directions orthogonal to both U1 and U2, the vector U3 point in the most significant direction, and so on. So we will use the eigenvectors U1, U2, and U3, which has these meanings: significant direction in decreasing orders. Here is one example. A data on a simple random sample of 100 bird species, and the three factors were measured: the length of a bird, and wingspan of a bird, and weight of the bird. So we have three factors. So does m is equal to 3, and we have n spaces here. So the matrix is a 3 by 100 matrix. So if we multiply the A transpose on here, then we will have 3 by 3 matrix, and like this. Then this 3 by 3 matrix, which is symmetric, this matrix has 3 eigenvalues like this, and we can find the corresponding eigenvectors. So you see, we have A times A transpose, so we can easily find the singular values of the original matrices, and by that way, and corresponding left and right eigenvectors. Okay, of this actually, of this matrix. Here, T, the total variance T is the sum of the eigenvalues. So the fraction lambda 1 over the sum of the eigenvalues for this special example is so U1 account for this fraction, which is 92.28%. The second U2, vector U2, is lambda 1 over the total variance T, so which is 7.32%. Then addition of these two are 99.4%. So the remaining principal component explains only 0.4% of the data. So these first two eigenvalues are most important, and its corresponding eigenvectors are stand for the principal axis. Okay. So in this example, the remaining principal component is negligible compared to the first two eigenvalues. Here, actually, we can think which of the factors, length or wingspans or weight, is most significant in determining a bird's size. Okay. Here, we were able to find the weight and wingspans, and the others are in the order like this. So when we measure this example, the weight and wingspans are most important, and we can ignore the other factor for these examples. So this is the key. Okay, I will introduce two more examples like that of the larger size. Okay. So we have covered the theory of PCA, and we had a practice to find the singular values and the corresponding eigenvectors. And so now, we see how this PCA works. Okay, in the PCA that we used, what was the assumption? So we did assume the relationship among the variables are linear, and the crowd of points in p-dimensional spaces has linear dimensions that can be effectively summarized by the principal axis. And if the structure in the data is non-linear, then the principal axis will not be an efficient and informative summary of the data. So we assumed the data are linear. And when should this PCA be used? In the community ecology, PCA is useful for summarizing variables whose relationships are approximated linear or at least monotonic. Okay. And PCA is generally not useful for ordinating community data. Okay. Here, the example, PCA of many soil properties might be used to extract a few components that summarize main dimensions of soil variation. Okay. So this PCA can be used in this case, these data, and may not be for all. Here and here are second examples of PCA, and this data comes from these web addresses, and we did have a practice to draw these data, and let's see. And this is a PCA example, and using R, the open source software, and actually I did use in Sage. Here, with these data, we could with this we could list those data, and also we could select those data in this way. And this is the code that they used to plotting those data with the like this. So it can classify the data with the colors, and so how it can be structured to see. And also this data shows the eigenvalues from the largest one to the smaller one. In here, the first two eigenvalues are much more important than significant to compare to the smaller one here, like this. And this, so this kind of code could be used to find the data visualization, and also to find the principal axis, and also to find the eigenvalues to visualize. So how we can choose the dimension reductions. Okay, so this is the data that you looked, and there are more references for the R, open source software R, and some other information related to this PCA. PCA tutorials are here. Anyways, here's another examples. TOEIC examples. Here, suppose we have a ball. The position of ball attached to an oscillating spring is recorded using 3 cameras, A, B, and C, and the position of ball tracked by each camera is depicted in each panel below. So this ball moves like this. Then three cameras recording the moving trace of this, like this. So with these data, we can use the principal component analysis to analyze the physical behaviors with the PCAs. And this is another example. And PCA of 16 habit variables, and this is a kind of dangerous flux data. From those data, with the same code of those, we could find the eigenvalues. So as you see here, the largest 2 or 3 or 4 eigenvalues are dominating the others, and so we can easily can decide how many factors can be used for our analysis, but still preserve the properties of the original data. Okay. So with this analysis, we can choose the number of principal component axes. Okay, these eigenvalues. This is an example of data. Then how the principal axis can be found from here. Then with this, we do the analysis like what we did. Then we choose which is we center the configuration, and then we find the principal axis. Then in the new axis is the principal axis and the second principal axis, and we can rotate like this, but in the new axis, and this still has the original information of this, but we could simplify and reduce all the size and computations in that way. And we do like what we did. We find the principal component, first principal component, and we find the second principal component, and so on, up to the proper number of principal axes that we like to choose in the way like this. And this is what we have done. And here, what that means is PC axes are a rigid rotation of the original variables, and PC1 is simultaneously the direction of the maximum variance and the least square line of best fit. Here, square distance of the point away from principal component 1 are minimized. So actually, this graph shows what is written here. And here. here. The basic idea of principal component is this. Principal component of X are uncorrelated projection Y of the data point X1 up to Xn onto some directions such that variance of Y is maximal. Okay. PCA also, so this PCA is also used in the computer vision for face recognition. And also this basic idea reflect the best affine approximation as well. So this is another way of explain the ideas of PCAs. And here, the one example, one application of PCA is the image recognitions. Like this, which is called the eigen pictures, eigen faces. This idea, and here in 1987, Silovich and Kirby tried to use the idea of PCA to compress facial images, and they introduced the term eigen pictures because it used the eigen values and eigen vectors to prepare the principal directions UI. And but an explicit face recognition algorithm was given by Turk and Pentland in 1991, and they renamed eigen pictures as eigen faces. Actually, a couple of years ago, this was one research experience for undergraduate student of math major. It was a junior student who actually did use the eigen face approach for the face recognitions. And face recognition using eigen face. The identified people by biometric method is limited, and computerized methods to perform the facial recognition are increasingly important. We used an existing database of image to generate a set of eigenfaces using principal component analysis. Okay. After reducing the dimension and extracting principal features, and we analyzed the performance of the method by comparing this to the images in the database. Okay. And the tools were used include applied statistical concept, and PCAs, and K-mean clustering, etc. Anyway, this student went to the Yale University to do study on big data now. Okay, so how we can use it? Suppose you are a casino operator and have a database of images of everyone that is banned from your casino. And for each of these, you use the Gram-Schmidt method to approximate the image as a linear combination of eigenfaces. Okay? So for each individual that walks through the doors, your security system would take a picture of their face and break that down into its eigenface component and compare it to all images in the database. So if it is close enough to one in the database for who are banned, then that person is banned from the casino. So this, like this, the principal component can be used in many ways. Okay, here, and so yeah, we have learned how to find, how to compute the dominant singular values of large unstructured matrices, and yeah, we did use the k leading eigenvectors of the matrix A, symmetric matrix A transpose to maximize the Rayleigh function under orthogonality constraint, and the Rayleigh quotient of non-zero vectors X of this was used in the algorithm of the optimal the optimization problems that we have seen, and I think that's it. Oh, the one other things that I like to add here is for finding eigenvalues and you must have heard the terminology of the companion matrix. When you have a matrix to find the eigenvalues, we found the characteristic polynomial like this. But finding the solution of this higher degree polynomial is still a big hurdle for us. But as you have done, the finding eigenvalues of a matrix, we already have developed many nice algorithms to find the exact the eigenvalues of the given matrix. Important thing is, from this polynomial, we can construct a matrix whose shape is like this. Okay, these AIs are here, and all others are 0 and 1s, like this. The interesting thing is, the characteristic polynomial of this matrix is same as this. So eigenvalues of this matrix is same as the solution of this, which is the eigenvalue of the original matrix, whose characteristic polynomial is like this. We call this matrix is a companion matrix of the polynomial P of x. Like this. So now finding the solution of this the polynomial of higher degree is the same as the finding the eigenvalues of this matrix with your knowledge on linear algebra. One other fact is, if the P of x is a monic polynomial, then the minimal and characteristic polynomial of the companion matrix of P of x is P of x itself. Okay. Here, you already know about the characteristic polynomial, and some of you may see this minimal polynomial for the first time. Okay. Is there anyone who can explain about these minimal polynomials? Okay, as we saw in the examples on the board, then now you know to find the minimal polynomial of a given matrix. All you have to do is find the Jordan canonical form of a given matrix, and then consider the largest Jordan block of each distinct eigenvalues. Then you use the size of those largest Jordan block as the exponent of each terms for each distinct eigenvalues. Then this matrix, the given matrix A, not only satisfies the characteristic polynomial, but also satisfies the minimal polynomials, which has the least degree that annihilating that matrix A. Okay, and okay, that's it. That's it about the eigenvalue and companion matrix and the relationship with the Jordan canonical form and minimal polynomial. So, with this knowledge, the problem of computing the roots of a polynomial reduces to finding the eigenvalues of the corresponding companion matrix, and even further with the characteristic polynomials. And actually, this is the proof of this theorem. Okay, here's the characteristic polynomial and the companion matrix, then this satisfies this. So if you summarize this, then it satisfies the characteristic polynomial, the matrix A, that satisfies the characteristic polynomials, and which says the characteristic polynomial of the companion matrix is the polynomial P of x, and also it is a minimal polynomial which has the least degree that satisfies the characteristic polynomials. So this is the matrix theory. I think we explained pretty much on the PCAs now, and we saw the examples, and we can find the principal component and eigenvalues, and with those the data, the eigenvalues, now we can decide how to make the rank reduction with this, and we could use the code that that visualize all those data that I will show. And these are the references. And now you summarize what you have learned on PCAs. Okay. And I asked you to review these materials on calculus, linear algebra, and statistics with R and engineering mathematics. And some of you already submitted your homeworks on this. I think now we are ready for the big data and machine learnings. And we will have a midterm examination just after this class. And it includes the PBL report of yours for the first 7 weeks, and all of your participation record in quantity and quality, and then summary of what you have learned for the first 7 weeks, and you approved the project proposal. And 3 of you already uploaded those in Q&A, and after the approval, then you will give a presentation, and it will be reviewed by each others. And we will cover the matrix and the graph after the midterm examination. And these are the materials. And this is what I have made for you. So we will start after the midterm examination. Here, this is the code that was developed by the director of the Big Data Center at Korean National Institute of Health, and we have the most of this big data research now are done by the R program, and these are the most of the R code that you have to know, and this is the lectures for the R programming and the how to use the R programs and the code. So you can easily find this. And nowadays, and Google and Facebook and many others are using more of R over the SPS and SAS. And many others also are following that trend. And here, we have given lectures. We have given 13 lectures of these from the introduction of big data, mathematics for big data, and LU. We covered the LU decomposition and SURE decomposition and power method, and QR decomposition, and the Google's page rank algorithm, and singular value decomposition, and least square solutions, and polar decomposition, and non-negative matrix factorization, and finding Jordan canonical form using a dot diagram, and finding generalized eigenvectors using a Jordan canonical form, and also finding Jordan canonical form after you find the generalized eigenvectors. And with those knowledge, we were able to define a matrix functions and by using the Jordan canonical form. And we covered the first and second part of principal component. And interactive statistics lab using R and Sage Math can be found on this web address. And there is a lab for math statistics that some of you already practiced. And the R program can be downloaded from here and can be installed in any of your PCs or laptop. And there are frequently asked questions that you can see, you can use, and also here this is the code that the code and output that I actually did practice all those with the data which was generated over the last year when we had the MERS disease, the infection, so for which was a big headache for the last 6 months. And so here, we had the code like this, and then the outputs like this. And here you will see how how those data can be visualized and used to find a meaningful decision for the next step. Here, with this R, instead of Sage, here we use R, and here the mean and standard can be found in here, then factors can be found here, and data can be visualized like this, and here, and you can say, you can allow the data here, and matrix can be made as a row and columns like this, and you can choose. So those are the commands that you can use, and these data comes from here, and you can find the size of the data from this command. So actually, this data is about more than 1 terabyte of those, and we only used here about only 1 week of the patient's record to deal with this. We could find the means and standard deviation and others here, and we could call what? We could use all these data, and we could here we could call a data file from so we use to utilize these data here, and here we could do. So just try to whatever you do, and you don't have to use this. This does have the limited the ability to deal with everything, because it's cloud computing facility that can be used by the mobile devices. But you just download the R program to practice all of them. It works perfectly in there, and we will go through how to treat the data, how to classify the data, and how to select the necessary data to visualize and to find to find whatever we need, eigenvalues and eigenvectors or principal axis, and you can visualize all those things. And so it all can be done with here. Okay. And package can be installed automatically with this command, and and plot can be done. And, I have worked to develop these tools, so it can have a full functions to visualize all the things. I will keep going to do so. Anyway, here this. As you see, that you will see all the data here, and what else? But here, Bayesian classifications, and okay, and these are the things that you can see. You all can be found in here, and also you can do practice it in the Sage server and the R program which is installed in yours. Then we will continue to this after the midterm. Any questions?